So our next speaker will be Priti Staab, who will be talking to us about protoclusters and if they are forming stars or not.
Share screen. Share. Oh. Yep. And then the green one is your browser pointer.
Hi everyone, my name is Priti Staab. I'm a graduate student at UC Davis. I work with Professor Laura Lubin, Dr. Brian Limo, and the CPVO team. Today I will be talking about protocluster mysteries. Is star formation dead or alive?
You can talk closer to the microphone.
So then you gotta use this one.
Is this one? Oh, yeah, that's right. This one? Yeah.
That one.
Okay, cool. Can you hear me? Okay. So starting with the cosmic web structure, here is a figure from Millennium to dark matter simulation, where on x-axis we have scale. So as we go from left to right, we're zooming in, and on y-axis we have redshift or time. So each row is cosmic web structure at different redshifts, and the blue regions are the overdense regions where filaments are intersecting. What I really want you to notice from this plot is how the contrast between the overdense regions and less dense regions are increasing as we go from top to bottom. So what is exciting is that we can construct these density maps at high redshift, assuming galaxies trace underlying matter fields. So here are just two examples of such density plots. Hyperion is a structure at 2.45. And protocluster, on the right-hand side, we have protocluster at redshift 4.57, which is the protagonist for our mystery today. And the red.
Your screen's not sharing.
Oh.
Let's stop and start again. There. Does that help, Mark? I think so. Okay. See if that helps. Okay.
Okay, so the color scale for both of the plots is basically the same. The red regions are the most dense regions and the blue regions are the least dense region inside the structure. But if you look at the numbers on the scale for the lower redshift or 2.45 redshift structure, the red regions are 5 sigma overdense, and at 4.57, the red regions are 3 sigma overdense. So we definitely see the contrast increasing observationally as well as we go towards lower redshift. So today I want to talk about the star formation activity that is happening inside this protocluster, as well as the galaxies that are around it. But before I talk more about that, let me, oh no, it's not working again.
No, it's not working again.
Nope.
No.
Oh, there we go. Let me contextualize what star formation rate density is. So star formation rate density is star formation rate per unit co-moving volume. And I am looking at the SFRD across the universe or history of the universe to see if I see some trends. And this plot shows different studies from 2007 to 2021 that use different techniques. So that's where all the different data points come from. They all use different techniques to find star formation rate density. And we can see that SFRD increases on this plot from redshift 0 to 2 or like 2.5. And then it either falls off or plateaus. So the dotted line is the best fit line from Maddow and Dickinson from 2014. And then these different data points at high redshift kind of suggest that maybe it doesn't really falls off, but it plateaus. So I'm looking at what the field galaxies around my protoclusters are doing on this plot. And then I want to go ahead and ask, well, how does overdense environment affect this trend? So looking at overdense environment below redshift 1.5 first. So these are the cluster environments, galaxies inside the cluster. And on y-axis, we have fraction of quiescent galaxies, which are galaxies that have stopped forming stars. And you can see that this fraction is much higher in overdense environment compared to the less dense environment for equally massive galaxies. This suggests that cluster environment is hostile for star formation rate or star formation below redshift 1.5. And we can assume that most of the star formation happened early on. We see hints of that from a simulation. This is a figure from Chang 2017. I'm only focusing on the blue line today, but on y-axis, we have fraction of cosmic star formation rate density from protoclusters, which are the overdense structures. And as we go towards higher and higher redshifts, we see that this fraction is increasing. So we see more and more star formation activity happening at higher redshift. We wanted to compare this observationally, which hasn't been done before. And to do that, we decided to start with the protocluster at redshift 4.57 because that was our highest redshift cluster. So our survey is charting cluster construction with Woods and Aurealis survey, which is over redshift 0.5 to 5, where the lower to intermediate redshift part comes from Aurealis, and higher, some of the higher redshift data comes from VMOS ultra deep survey. So using Woods, we discovered over 50 spectroscopic overdensities. And as I said, we decided to start with the redshift at redshift 4.57 protocluster. So we followed up this protocluster with Keck. We spent over 30 hours on just this protocluster alone with Demos. This is the sky plot of this structure. All the rectangles are different mass that we use. And on the left-hand side, you just see me be crazy happy that I got to visit Keck. So we have over 50 confirmed galaxies, protocluster galaxies that we have confirmed spectroscopic data for. And our photometric data comes from the Cosmos field. So this is our targeted region. And this survey has over 40 bandpass filters, and it ranges from far UV to IR. So we're using Cosmos 2020 catalog. Some of it is Cosmos 2015, and also photometry from KPAC 2007. And we are matching this photometry with our spectroscopic data by using RADEC of galaxies within sky error of 0.3 arcsecond. So just to remind you again, this is the protocluster that I'm talking about. This is what it looks like. All the galaxies inside this structure are the protocluster galaxies, and the galaxies around it are the field galaxies within a certain redshift range that we decided. So now we have our data, we have the region, and we want to look at the star formation rate of these galaxies. One of the most efficient and best approaches at high redshift to do this is using SED fitting, where SED stands for spectral energy distribution. And it is the distribution of electromagnetic radiation that comes from galaxies across the field wavelength. So in this plot, this black line here is the spectrum of galaxies at redshift 4.55. This plot is generated using Sigale, which is the software I use to do SED fitting. The purple points are the observed data points, and the green and the blue parts are the contribution from different physical processes that take place in the galaxy. So basically, SED fitting helps us go from our photometric data to the physical properties of galaxies, such as star formation rate and stellar mass. So now that that method is, I specified the method, we actually start with the PDF of Redshift, where we sample the PDF using Monte Carlo, and we fit all 100 of the iterations using SED fitting to get PDF of star formation rate. I should mention that we also extrapolate our results to low luminosity galaxies using Schechter luminosity function. So we found that our SFRD for the field galaxies does agree within the error bars, and the error bars on our results are actually not final yet. However, generally, it does agree with the data point using Alpine, which is a large field survey at redshift 4.5. And so that tells us we are not doing anything crazy. Our methods are kind of aligning with other results. So now I want to look at how is the environment driving these trends? Or what happens to this result when I look at the protocluster SFRD? And turns out it is literally off the charts. So the SFRD inside the protocluster is much, much higher. And this tells us that environment is a key factor in driving the star formation rate density. And when we compare that with the simulation, again, we see that our star formation is definitely much higher when we go towards higher redshift. At redshift 4.57, assuming that our protocluster is a proxy of all the protoclusters at this redshift, almost 50% of the entire star formation rate density in the universe is coming from overdense environments. Now, this might not be true. There are some caveats to these results. And it's that our protocluster is really massive. It's 3 to 4 times more massive than a typical protocluster at this redshift. And so that might be why we see such a discrepancy between the simulation and our observational result. But on the other hand, we might also be missing the contribution from really starburst galaxies, which make them diminish in UV and optical. So this result might be even higher than what we see here. So this is for my thesis. This is just where we are starting. In future, we would like to expand this work for our other our other protoclusters, which we already have data for from Keck. Shout out to Priti, who helped us take some of this data. And we want to continue this analysis with all these protoclusters to see or better understand the relationship between SFRD and the environment. So that being said, I will leave up my summary slide and I'm happy to take any questions.
Are there any questions? So I have a few questions. So how do you, what criteria do you use to distinguish between field and protocluster members?
So you repeat the question, no one else.
Yeah, sorry. What is the criteria that we use to separate our field galaxies and our cluster galaxies? So our criteria is basically all the galaxies that are going to fall into our protocluster region that have a certain overdensity higher than the field galaxies. So right now we are using redshift as a rudimentary method to redshift and RA index to define our volume for the protocluster. But in future, we're going to look at the actual structure, like overdensities using VMC method, which is the Monte Carlo method.
John?
So
Yeah.
you have Cosmos or similar other things for most of these fields. Is there anything interesting in the morphology of the galaxies themselves that gives you any hints about what's going on here?
So the question is there anything interesting in the morphology of the galaxies that would tell us what's going on, right? It's hard to see morphology of galaxies at such high redshifts. But if you look at the color diagram, which basically tells us, are these galaxies red or blue, which is one of the criteria to define if galaxies are dead, quiescent, or forming stars, we see that inside our protocluster, all the galaxies are forming stars. So we cannot look directly at the morphology of galaxies, at least using the data we have, but yeah, that's the general trend we've seen. Yeah.
Yeah.
The models that you use to estimate your SFR similar to whatever the field work was done in before. So I thought they were.
Right. So okay, the question is, are our models to do the SED fitting similar to the other studies that we saw it on the plot that I'm comparing my results to? And so all those models, all those studies are actually using different techniques, like using UV luminosity that is dust corrected, or re-emission in IR, or some are using C2 line or gamma burst. So I cannot speak directly about their SED fitting, but we are using delayed star formation history. Yeah, but we did make sure that our base point is the same. So we are we are taking into account all the contribution from lower luminosity galaxies. So that part is definitely missing.
Yeah,
You said this was a pretty massive protocluster size, or did the redshift you recall what the would be at redshift 0? Or did you calculate that?
Yeah, so it's at redshift 4.57, it's almost 10 to the 13.5 solar masses. And by redshift 0, it's predicted to be 3 to 10 times 10 to the 14 solar masses. Sorry, I did not repeat the question.
okay, we'll probably have time for one more question, so I'll have a question.
Okay.
So when you do the spectroscopy sampling, are you sampling all the space that you would like, or, I mean, what's the percentage? You something like 80% of the protocluster when you get the spectra, or 100% of the?
It's 50%, I think.
Okay, so
What was Priti's question?
Sorry, the question was, what is the sampling rate inside the protocluster?
Spatial, are you sampling the whole protocluster or just a section of it?
Oh, yes. So the question is, are we sampling all of the protocluster? And the question is, yes, using our 6 different masks, we did sample what we see is like the whole overdensity, so the protocluster.
And that's defined based on the simulation. So you use the simulation to tell you what the extent is.
No, so the question is, does the simulation tell us what the extent of the protocluster is? And the answer is no. This structure was discovered using Woods, where they looked at 10,000 galaxies between redshift 2 and 5. And we actually used the VMC technique to understand which galaxies would fall inside our cluster. And yeah, sorry.
Thank you.